This waterway is not simply a channel. It is a controlled staircase carved across one of Earth's hardest crossings.
Ships do not cross Panama by brute force alone. They rise, float, descend, and obey gravity.
Every stained wall and waterline mark records a century of vessels being lifted over continental rock.
Here, at Culebra Cut, engineers sliced through the Cordillera Central, where rain could turn progress into collapse.
The canal depends on water, but Panama's water was also its threat. Sudden, heavy, and relentless. From the Atlantic to the Pacific, the canal is a machine disguised as landscape. The ship appears powerful, yet inside the locks, it becomes a carefully guided passenger. The scale feels unnatural because ocean trade is passing through a corridor once ruled by mud and mosquitoes.
To understand how it exists, we must first return to a landscape that resisted every straight line.
Before concrete and steel, the isthmus was a humid maze of rivers, hills, insects, and unstable ground.
Maps made the distance look narrow. The ground made every meter expensive, slow, and uncertain. The Chagres River could feed a canal, but in flood, it behaved like an engine of destruction.
Across the route stood the Continental Divide, not high like the Alps, but stubborn, wet, and fractured.
The canal's story begins with one question. How do you move oceans through a mountain?
For empires and merchants, Panama promised a shortcut between oceans, avoiding the long, dangerous voyage around South America.
Before the canal, ships rounded Cape Horn, where distance, storms, and time taxed every cargo and crew.
Ferdinand de Lesseps had conquered Suez, but Panama was not a desert waiting for a trench. The French first imagined a sea-level canal, a direct cut through land that refused to stay still.
Steam machines helped, yet mud swallowed rails, rain filled excavations, and slopes slid back overnight.
The problem was not only digging earth, it was preventing the earth from returning.
Without knowing mosquitoes carried disease, even hospitals accidentally created water where infection could breed. Yellow fever and malaria weakened crews faster than the shovels could advance the line.
Each flood stopped transport, and without transport, excavation became a pile of earth with nowhere to go.
The French project bled money, confidence, and lives until engineering ambition could no longer hide failure.
When the first attempt collapsed, the jungle began reclaiming machinery left in rust and silence.
The next builders inherited not a blank landscape, but a warning written in abandoned cuts. The solution would not be a sea-level trench. It would be a water-powered lift system. Instead of fighting the Chagres completely, engineers planned to trap it and make it work.
Before excavation could accelerate, the railroad had to become the project's moving skeleton.
Panama's rain forced every design to answer one question first: where will the water go?
Culebra was not one solid wall. It was layered earth and rock, weakened by water and vibration. The work demanded not one invention, but a system: digging, hauling, draining, blasting, and surviving.
By night, the impossible problem remained outside the barracks, soaked, buzzing, and waiting for morning.
To cross Panama, the builders would have to organize people and materials as precisely as water. Most hands that built the canal came from the Caribbean, arriving with little more than tools, clothes, and hope.
Behind every machine stood human labor, clearing mud, repairing tracks, loading stone, and enduring heat.
Work camps became temporary cities, feeding thousands whose strength had to be renewed every day.
Rail lines were constantly shifting because the cut itself kept moving forward and falling apart.
Steam shovels bit into Culebra, each bucket turning mountain into cargo for the railroad.
Excavation mattered only if spoil left quickly. Delay could choke the entire operation.
Millions of cubic yards removed from the cut became embankments, fills, and new ground near the Pacific. Where shovels could not cut fast enough, dynamite fractured rock into pieces the machines could lift. Drillers opened holes by rhythm and weight, preparing the mountain for controlled explosions. Each blast had to break rock without burying tracks, men, or the machines needed next.
The canal consumed metal daily: teeth, cables, rails, wheels, bolts, and boiler parts.
Beyond the cut, another material defined the project: concrete poured in quantities never before attempted there. Aerial cableways carried concrete across lock sites, turning empty forms into enormous hydraulic chambers. Before concrete hardened, carpenters shaped its future with timber, wedges, rope, and patient alignment. The workforce was organized but unequal. Wages, housing, and risk were divided by race and rank. Public health became engineering too, because a canal could not be built by a dying workforce. Greens, drainage, oiling, and fumigation turned disease control into daily routine. Progress came from repetition. Load, move, dump, repair, drain, blast, and begin again.
The canal's scale is measured in machines, but its reality lived on exhausted human faces.
By 1907, the project had become less a construction site than an industrial organism.
The breakthrough was conceptual. Lift ships to a lake, carry them across, then lower them again.
Gatun Dam would hold back the Chagres, creating a lake large enough to become the canal's summit.
To control the river, builders first had to redirect it through temporary channels and protected banks.
As the valley flooded, old routes disappeared and new rail lines climbed above the rising water.
The dam was not a wall of stone, but a broad earth structure built by controlled layers. A lake that lifts ships also needs a spillway, because excess water must leave safely. At Gatun, 3 lock chambers would lift ships in stages from sea level to the lake. Concrete walls had to be massive, accurate, and smooth enough to guide moving water and steel.
Hidden beneath the locks, culverts and valves would move water without pumps, using gravity.
Valves were the canal's quiet muscles, opening and closing the movement of millions of gallons.
The miter gates worked like giant doors, sealing chambers against the pressure of changing water levels.
When filled correctly, the water rose evenly, carrying a vessel upward without lifting machinery.
A ship inside the chamber became a floating weight, lifted by the very water it displaced. On the Pacific side, Pedro Miguel formed one step between the lake system and lower waters.
At Miraflores, engineers also had to account for Pacific tides, which changed far more than the Atlantic.
Material flowed like a second canal: stone, cement, steel, timber, fuel, and replacement parts. Train scheduling became critical because a blocked rail line could stop an entire excavation phase. Culebra became a terraced industrial canyon, with machines working on levels cut into unstable slopes.
Drainage was constant engineering maintenance, reducing the water pressure that triggered dangerous slides. Even with care, the ground moved. Survey stakes revealed slopes creeping toward the cut.
Slides were not interruptions. They became part of the workload, adding millions of yards to remove. The cut advanced by inches and buckets, turning geological resistance into a measurable schedule.
Where water already filled the roof, dredges continued the excavation beneath the surface.
Approach channels had to be deep and stable, allowing ocean vessels to reach the lock system safely. The artificial lake transformed the route, replacing miles of cutting with a navigable inland sea.
Electrical controls linked gates and valves, giving operators coordinated command over enormous moving parts. Only when pressures balanced could the gates open, chamber by chamber, step by step.
Locomotives did not pull ships across Panama. They kept them centered inside the locks. Small leaks mattered. because reliability depended on details hidden beneath the canal's monumental scale.
When excavation reached its level, water entered spaces that had consumed years of blasting and hauling. The mountain had not vanished. It had been reorganized into a narrow, controlled passage. Now the system made sense as one machine: Atlantic locks, Lake, Cut, and Pacific locks. A vessel crossing the isthmus proved that the idea had become an operating reality.
The impossible had been solved not by one heroic act, but by thousands of linked decisions.
But the canal's success cannot be separated from the lives spent to make it possible. Falls, explosions, derailments, and rock slides made the worksite dangerous even when disease declined. The railroad that enabled speed also carried risk, especially on wet grades and shifting ground. Sanitation campaigns were intrusive and relentless, yet they changed the odds of survival.
Medical knowledge turned invisible enemies into mapped problems, breeding sites, fever cases, and control zones.
For many families, the canal was not a triumph, but an absence that never returned home.
Survival also meant ordinary acts: washing mud away, writing letters, repairing clothes, sleeping when possible.
The canal was built by people who carried exhaustion quietly between one shift and the next.
Nature did not surrender once. It had to be answered again after every slide and storm.
The achievement was inseparable from inequality, with the hardest risks often carried by the lowest paid workers.
As mosquito control improved, fear remained, but the daily numbers began to change. Completion did not erase the cost. It fixed that cost permanently into concrete and water.
When the first passages came, pride and loss stood together along the same waterline.
The canal's walls bear no names, yet they were shaped by countless anonymous hands.
A new lake covered valleys, villages of work, railbeds, forests, and memories beneath calm water.
What was once sacrifice and experiment became a permanent route through the world's trade.
Today, the canal still works by the same principle: controlled water lifting global commerce over Panama.
Modern controls are digital, but operators still manage gravity, gates, timing, and narrow margins. Culebra's scars have greened, yet the cut remains the canal's most visible act of force.
Even now, passage is a choreography of pilots, tugboats, locomotives, signals, and patience.
The expanded canal added new locks, proving the original idea could still adapt to larger ships.
Its future depends on rainfall, because every transit spends fresh water from Panama's lakes.
The canal is powerful, yet vulnerable. Its engine is not steel, but stored rainwater.
A cut through one isthmus reshaped distances between ports, markets, navies, and supply chains.
For Panama, the canal is not only infrastructure, it is territory, memory, revenue, and identity. Control eventually returned to Panama, making the waterway a symbol of sovereignty, as well as engineering.
Day and night, the canal repeats its quiet ritual: fill, open, guide, lower, release.
The old concrete still works, because maintenance became part of the canal's original promise.
Each transit is ordinary now, which may be the most extraordinary proof of the engineering.
Panama was not split apart casually. It was measured, flooded, cut, locked, and paid for.
A continent was not defeated here. It was negotiated with water, labor, concrete, and time.